Yeah, I hope I'm audible. So, so last week we looked at controllable systems and controllability and how to decompose into the controllable decomposition and did sorry stabilizability and things like that. So this session we'll look at the dual of that. So dual is essentially observability. Okay. Uh, so we'll be looking at systems like AX and Y equal to CX. I'm not considering BU here. So it doesn't matter if this is there or not, the analysis remains the same. So X dot equal to AX, Y equal to CX. So, so what essentially is observability? So observability means, let's say you have a trajectory, okay, from T1, T0 to T1, okay. So, so what is this trajectory given by? E raised to AT minus T0 X naught. This is my trajectory, okay. That is essentially my phi times X naught, okay. So what is, so I am able to see a certain part of the trajectory, okay. I'm only able to see a certain part of the trajectory, okay, T0 to T1. So it's not exactly this trajectory, it's some, it's some linear combination of the trajectory if you want to see, if you want to think of it like that. So this is my y of t, this is my x of t, okay. So y of t is related to x of t by this linear combination, this matrix C, okay. So y equal to C times phi x naught, okay. Now my objective is to find x naught from my given y, okay. So how do I do that? Because C may not be even invertible all the time, okay. So yeah, if C is, let's take an example, y equal to I'll just take, okay, x dot equal to ax and y equal to some 2 0 where x belongs to some r2, let's say this is 0 3 times x, okay. So then x naught is pretty straightforward to compute, right? X naught is nothing but C inverse phi inverse y, correct, because C is now invertible. It's just 1 by 2 0 0 1 by 3 times e raised to minus a t minus t naught times y of t. This is exactly my x0, correct. So yeah, so that's x naught. So but C need not be even square to begin with, okay, need not be even square. So usually C is some R P cross N matrix, where P is often less than N, because you won't always buy sensors for all the measurements. You usually buy a velocity sensor and estimate the position and things like that, okay. So can you even estimate position in certain cases from velocity? That's the goal of this this lecture. For that we need to first identify what is not observable, okay. So before going on to observability, we have to first identify what is not observable. So that's why it's called the dual of the controllability, because earlier we checked what is controllable, okay. Here we are going to check what is not observable. So let's take two time instance t0, okay. Then the unobservable subspace, okay, is given by set of all initial conditions such that C phi x naught is 0, okay. Basically this x naught is in the null space of this matrix, okay. For all time t belongs to this. So what happens is, earlier we plotted this trajectory, right? You have x of t, okay. So if you apply this transformation C times phi, it goes to the origin, okay. So I'll just do it in a better way. So you have a transformation C times phi, you get 0. That is my unobservable subspace, Okay. Now you see you are finding the initial value from from your future outputs. Okay. So y of t belongs to t0 to t1, which is your future compared to x naught of t naught. Okay. So based on this entire trajectory, you want to compute what is x naught. Okay. So when can you say this is observable? When can you say the system is observable? When the unobservable subspace is nothing but the origin. Okay. So why is that? Let's say there is some unobservable vector, a trajectory inside this unobservable subspace. Now if you want to estimate y equal to c phi x naught plus some linear combination of xu. What do you get? You get c phi x naught plus, I'll call this c bar or something, or alpha, I'll call this alpha c phi xu. Now we know xu belongs to this set, which means this is 0. So you can't have a unique solution. That's what it means. Okay. If there is something in the kernel of a matrix or a transformation, the solution won't be unique. That's your basic linear algebra. So that's exactly why there shouldn't be anything other than the 0 vector. Okay. Yeah, so that's the thing. So we'll look at an example of that, but before that we have to define unconstructible subspace as well. Okay. So unconstructible means it's the it's something like reachability. Okay. Based on your past values, you have to predict not predict actually, you want to find the future state. So y of t is given by c phi t1 x1. Okay. You can verify this. Okay, if this is true or not. This is just by taking x instead of t naught. If you take t1 here, you are basically going against the flow. That's what it means. Okay, t1 t0. Okay. So this is your y of t. Now the same conditions apply, where unconstructible subspace is set of all x1 such that c phi x1 is equal to 0 for all t belongs to t0 t1. Okay. So so I hope yeah, again it's constructible if uc is 0. Constructible if and only if uc is 0. Okay. So those are the two main subspaces. When you see the observability compared to your controllability, what we wanted was the observable subspace should be the controllable subspace should be the entire Rn. Okay. Here unobservable subspace should be the kernel of the unobservable subspace should only be 0. Okay. Okay, did I say kernel? I think it comes later on. It's not the kernel, it's just your set. So it should contain only the 0 vector. Okay. So that's the thing. Now, okay, as we defined in controllable subspace also, we have to define something called the gramians. Okay. Gramians denote your energy in the trajectory or your input. In this case, it's the energy in the trajectory, okay, or your output energy. You can equate it to your output energy. Okay. So or the inverse of output energy, just like how we saw in the previous class, where your the energy required to control was maximum in the direction where lambda, the eigenvalue of the gramian, was less. Similarly, this is like your output energy. Okay. So so it's just like your controllability gramian, and it's defined in the same way, just that it will be a dual version. So t0 to t1 e raised to a tau minus t naught transpose c transpose c times e raised to a tau minus t naught d tau, and constructibility gramian is same t0 to t1 e raised to a transpose tau minus t1. So this looks at all the future, this looks at all the past. Okay, that's the only difference. C transpose C e raised to tau minus t1 d tau. Okay. So yeah, so now it's similar to your controllability. Controllability was your image of, I'm just writing a side note here, so it's just a side note. Controllability was your controllable subspace is same as image of controllability Gramian, right? So what is the dual of this? The dual of this is nothing but observability, where your unobservable subspace is the same as kernel of the observability Gramian. Okay, same way you can write it for reachability and constructability. Okay, so this is your kernel. So which means the kernel, so we said that u0 must only be the 0 vector, which implies the kernel of w0 must be equal to 0. Okay, which means the rank of w0 must be equal to n. Okay, so that's your definition. Now I think you can prove in the same way that unobservable subspace is also the kernel of your C, Ca, etc., Ca raised to n minus 1. This is your unobservable subspace. Okay, it's the same as kernel of. Okay, so I think this you can prove for continuous time LTI systems. For discrete time, the only difference is all these integrals become summations, and for constructability, the matrices A, K minus 1, etc. needs to be invertible. Okay. So the thing is, if they are not invertible, you can't go against the flow, right? Because how do you write x of k equal to a raised to k into x of 0, correct? So if you want to go against the flow, what will you do? A raised to minus k, that's all. So this has to be invertible, that's the logic. Okay, so A has to be invertible for going against the flow. So it's the same logic for your reachability also. Okay, yeah. So okay, now maybe we'll do a problem, then we'll come back. So just a second. So I'll just show what how this is. So let's take A and B. So I'm not taking any B matrix as of now. It doesn't change the analysis, it just makes it harder, that's all. So okay, there's no comma here. Okay, so this is my discrete time LTI systems. Okay, so let's I got some values. Okay, I don't know what the states are, I just got some values. Y of 0 is 1, y of 1 is 0.8. Okay, I have these two values. Okay, so what is my x of 1 equal to a times x of 0. Okay, y of 0 is c times x of 0. Okay, and what is y of 1 equal to? C times x of 1, which is same as c times, I'll just substitute this here, that is c times a times x of 0. Okay, so what is, I'll just write this in a matrix form. This is nothing but c Ca times x of 0. Okay, so now you know why this matrix must have full rank. That is because you need to invert this matrix to get x of 0. Okay, so what is my C matrix? 1 0. What is my C times A? So C times A will be, so if I just multiply this, 0.2 and the other one is 1. Okay, times x of 0. Now this is invertible. You can see that these, no, it's invertible. So what is my x of 0 equal to? 1 0 0.21 inverse y of 0 y of 1. So what is that inverse equal to? 1 by, so it's just 1. So determinant is 1 and this is 1 1 0 minus 0.2 times what was y of 0? 1 and 0.8. Okay, so this is nothing but 1 minus 0.2 plus 0.8. So am I doing any mistake here, or is it correct? I think there is a negative sign here, right? Yeah, there is a negative sign here. Okay, so this is nothing but 1 and 0.2. So is there something wrong? Okay, sorry. There was a negative sign here as well. Okay, this is minus. Yeah, so this is now 0.2 plus 0.8. It's 1, right? I think it's 1. Okay, so yeah, just let me know if there is some mistake. But yeah, the logic is you have to basically invert this matrix and multiply it with y0, y1. In the continuous time case, you have to do it as an integral. It's not a step. Okay, so in the continuous time case, it will be an integral. Okay, which is exactly your Gramian. Okay, so yeah, so that's the logic. Now let's look at a case when I take a different sensor. Okay, let's take 0.2, 1, 0, 0.5. I think this should be minus 1. Okay, I am not sure, but there is some, maybe if I do it again, I'll just write this again. Let's make sure there are no mistakes. I'll just write that again. So what is x naught equal to? The inverse of this matrix. So if I calculate the inverse, it's nothing but so 1, 0, 0.2, 1. So the inverse of this is, I think it's this itself, times 1, 0, 0.21, that is nothing but 1, 0. Yeah, it's not the inverse. So there needs to be a negative here, right? Yeah, so there is a negative there. Okay, so I think this is the inverse, 1, 0 minus 0.2, 1. Okay, yeah, is that the negative? Okay, anyways, so this is y of 0, y of 1, which is equal to it was y of 0 and y of 1 and minus 0.8. So this is nothing but 1 minus 1. Okay, that is correct. Okay, so now my x of 0 is this. Now let's take a different sensor. I'll just write this again, where your A matrix remains the same, 0, 0.5. Okay, and C matrix I am taking it as the other state. Okay, 0, 1. So now what happens is, let's take the same logic. So now I find y of 0 to be 1 and y of 1 to be minus 0.5. That's what I got from using this sensor. Okay, so what is this equal to? Y of 0 is C times x of 0, y of 1 is equal to C times x of 1, which is C A x of 0. So which means 1 minus 0.5 is be equal to C A is 0, 1, that is 0, 0, 1, that is 0.5 times x of 0. Now the thing is, let's take any vector xu equal to 1, 0. Okay, some alpha times 1, 0. Now the problem is, so xu plus alpha times 1, 0. Okay, so I am taking this is equal to 0, 1, 0, 0.5 times what is xq, x0 plus alpha times this. This is nothing but x0 plus alpha times 1, 0. So this is nothing but again 0, 1, 0, 0.5 times x naught plus 0, because this matrix multiplied by this vector is 0, which means I don't have a unique solution. This is not invertible, there is something in the kernel. So kernel of this CA is equal to 1, 0. So any vector, any trajectory on this axis, 1 0 axis, okay, I'll take a better color. So on this axis is unobservable, okay. So which means if any vector is there in this, okay, you can't actually reconstruct the state from the output, okay. That's why it's called unobservable. So any vector in this space, in this orange, the x-axis, you can't reconstruct, okay. It will go to 0 because 2 0 is same as 1 0 if you look at it from the output point of view. It will be always 0, okay. Your output will be 0, okay. That's the thing. So yeah, so that's one thing. Now let's compute the Gramian. I'm giving a different system, -2 1 0 -1, and C is same as 1 0, okay. We'll see using MATLAB also how to do that, but let's just for understanding, I'm taking T0 to be 0, okay, and T1 to be T1. I'll just tend to infinity later on. So 0 to T1 e raised to A transpose tau minus T1 C transpose C e raised to A tau minus T1 T tau. Now what is e raised to A transpose? So before that, what is e raised to A? AT. This is nothing but e raised to minus 2t, okay, 0, e raised to minus t, and what about this term? This is e raised to minus t minus e raised to minus 2t. You can just verify this because this is one of the system is decoupled, it is very easy to solve, okay. So this is your e raised to at. So now I find w naught equal to 0 to t1, the transpose of this e raised to minus 2t, e raised to minus t minus e raised to minus 2t, 0 e raised to minus t times C transpose is 1 0, okay, times 1 0 times e raised to minus 2t, e raised to minus t minus e raised to minus 2t, e raised to minus t, 0, and t tau. So this is equal to t0, so which is 0 to t1 e raised to minus 2t and e raised to minus t minus e raised to minus 2t, okay, and same will come here also. So this is e raised to minus 2t, the other one is e raised to minus t minus e raised to minus 2t, okay. So this is equal to 0 to t1. The matrix is e raised to minus 4t, e raised to minus 2t minus e raised to minus 4t, okay. Is this 3? I think it's 3t, yeah. Now it's e raised to minus 3t minus e raised to minus 4t. It's always symmetric. The Gramian is a symmetric matrix, so yeah, so you can prove that it's symmetric. And this is e raised to minus 2t. Let me just check that again. E raised to minus 2t minus 2 e raised to minus 3t plus e raised to minus 4t, okay. So now you integrate, I mean it's just exponential, so it's very easy, minus e raised to minus 4t by 4, okay, e raised to minus 3t by minus 3 plus e raised to minus 4t by 4 minus e raised to minus 3t by 3 plus e raised to minus 4t by 4 minus e raised to minus 2t by 2 plus 2 e raised to minus 3t by 3 minus e raised to minus 4t by 4, okay. You can just find the determinant of this, okay. So this is from 0 to t1, okay. You can immediately find the determinant of this and verify that it's always full rank, okay. No matter what t1 is, it's always full rank. You can actually check that using the determinant of this matrix, okay. So now I'll just substitute t1 infinity and t0 is 0, okay. So what will I get? The matrix will be negative of whatever I substitute for 0, so that will be 1 by 4, correct. Then this is 1 by, this is minus 1 by 3 plus 1 by 4, I think. Okay, so there will be plus and minus here. Then you have 1 by 3 minus 1 by 4, it's a symmetric matrix. Then this is 1 by 2 minus 2 by 3 plus 1 by 4. Okay, so that will be equal to 1 by just a second. So am I missing a 2 somewhere? I'm not sure. Am I missing a 2 somewhere? Just a second. No, I think it's correct. Oh, I think it's correct. Just a second. Let me just verify that. By the time maybe you can verify if whatever I have written is correct. I'll just check that again. Minus 2, 1, 0, minus 1. Yeah, I think it's correct. Yep. Yes. Yeah, I hope it's correct. You can just let me know if there is some mistake. I'm just having a small doubt. Okay. So yeah, so okay. I think that's correct. 1 by 4. Then this is 12 by 1 by 12, correct. This is again 1 by 12. This will be I think it's 24 and it's 2 12 minus 16 plus 6, I guess. Yeah, so that is equal to 1 by 4, 1 by 12, 1 by 12, 1 by again 12. Okay, I'm not sure about that, but okay. So this is actually invertible, and let's take the second case when c was equal to 0, 1. So what will happen? So this will be e raised to minus so is it minus 2t or minus t here? Did someone calculate that, or if someone has calculated that, maybe. Okay, let's just assume e raised to minus 2t. Okay, anyways, if someone has calculated, then just you can unmute and say, okay, or else we'll continue. E raised to minus t minus e raised to minus 2t, 0, e raised to minus 2t, 0, 1, 0, 1. This is a transpose here, right? Yeah. So this is e raised to minus t minus e raised to minus 2t, 0, e raised to minus 2t, 0, e raised to minus 2t, 0 to 0. Okay, so this is equal to 0, e raised to minus 2t. In the second case, it's 0, e raised to minus 2t dt. So this is same as t0 to t1, 0, 0, again 0, e raised to minus 4t t. So this is nothing but 0, 0, 0, e raised to minus 4 t by minus 4. Okay, so this will be equal to 0, 0, 0 as t tends to infinity. So from 0 to infinity, what I am getting? So this is nowhere invertible, right? For whatever value of t, it's not invertible because there is a column of zeros, and in fact, I mean, the rank is so the rank of this is at most 1. Okay, so this is, so you will get 1 by 4. Okay, so you can see what is the kernel of this. Kernel of W0 is nothing but the vector 1 0, which is exactly what we got earlier also, right? So the kernel of this W0 is same as your unobserved subspace. Okay, so yeah, so that's the thing. So we have shown that now. Now next, what do we want to do? We'll so we did duality, we did discrete time. Now yeah, if you have any doubts still here, you can unmute and ask, because it's the same as, you know, controllability. It's just that there are transposes, and instead of image it's kernel. That's the only difference. Now we have tests for observability. So what are the tests? It's again pretty straightforward, nothing fancy. The first one is of course the Kalman test, okay, where rank of C, CA, etc., CA raised to n minus 1 is equal to n. We saw why it has to be n just now. Second test is eigenvector test. So observability means you have no eigenvectors of A in kernel of this observability matrix. Okay, sorry, kernel of C. Okay, so why is that? That also we saw, right? Let's take the same example, minus 2, 1, 0, minus 1. What are the eigenvalues? Lambda 1 is minus 2, lambda 2 is minus 1. Okay, correct. So okay, so what are we, so what is V1 equal to? V1 is such that A minus lambda I. What is A minus lambda I? A, so I'll just do that. That is 0, 1, 0, minus 2, minus 1 plus 2 is 1. Okay, times V1 is 0. So what is the, and your C matrix was equal to 1 0 in this case. So what is the eigenvector? V1 is 1 0. Okay, and for V2 we have to take A minus lambda 2I, which is minus 2 minus 1, that is minus 3 minus 1 0 0. Okay, so V2 is something like I think it's minus 1 itself, not plus. Okay, so this is minus 1. So V2 is nothing but 1 minus 1, correct? So this is your eigenvector for the second eigenvalue. So what is, so is anything in the kernel of 1 0? No, because C transpose V1 is not 0. C transpose, or C times V1, because there is already transpose, C times V2 is not equal to 0. Now when can this be 0? When C is equal to 0 1, then this won't be 0. So C times V1 will be equal to 0 when C is equal to 0 1. When else can that happen? When C is equal to 1 1. Okay, when C is equal to 1 1 also that can happen, because 1 1 times 1 minus 1 is 0. Okay, so then it's unobservable. So yeah, so that's the case. So in this case, whenever C is equal to span of or C equal to some alpha times, I think it's 0 1, or C equal to alpha times 1 1, the system is unobservable. Okay, for these two conditions. Okay, so that's the case. Now the other test is, next test is the PBH test. Okay, PBH means rank of A minus lambda I C must be equal to n for all lambda belonging to the complex plane. And do you have to check for all the complex plane? No, because lambda only the eigenvalues can make this lose rank. Okay, so you don't have to check for all the lambdas, you can just check for the eigenvalues. Okay, it's the same as your controllability matrix, controllability PVH test. So yeah, if you want we can do that same problem. So what is A minus lambda I? In the first case we already found that A minus lambda I is 0 1 0 1, and what is C? C was 1 0. So the rank is 2. Okay, and the second case A minus lambda I C was equal to 0, sorry, I'll just minus 1 0 0, minus 1 0 0, and C was 1 0. Okay, so the rank is 2 again. Okay, the only case when happens is C is 0 1 or C equal to 1 1. Okay, so in those two cases PBS test fails. Now there is the fourth test, which is the Lyapunov test. This will only work if A is a stability matrix. Okay, if when A is Hurwitz, that's a very important part, because in sometimes people might miss this out. A should be Hurwitz, which means all the eigenvalues should have real part less than 0. So when A is Hurwitz, if observability implies there exists a W which is unique such that A transpose W plus WA equal to minus, is it C transpose or C transpose C? I am always confused. I think it's C transpose C, is it? Minus C transpose C. Okay. So I mean this is just like your Lyapunov for stability, where if you take C equal to so if you take C transpose C is equal to identity, then this just becomes A transpose W plus WA is equal to minus I. So now so what is this W? This W is W naught when T1 minus T naught tends to infinity. Okay. So what does this mean? This W is essentially represents your energy function, right? Because in Lyapunov stability analysis we showed that X transpose Px is something like a energy function. So in the same way X transpose this Wx will also represent some sort of an energy function. Okay. So in the last class we saw how this Gramian transform this circle into an ellipse. Okay, W times X, you take any vector X, you will get W times X. Okay. Now whatever happens, if it is full rank you will get an ellipse. So there will be a major axis and a minor axis. This will be lambda 1, this will be lambda 2. Okay, this will be scaled by lambda 1. So let us take this axis and I will take this axis. Okay. So let us take this as V1 and this as V2, this is lambda 1 V1, this is lambda 2 V2. Okay. So in this direction you need lesser energy. What is energy in this case? Y transpose Y. Okay. Or you can write like this, these are the same. In this case the energy is the output energy, not the input energy. The earlier the controllability case we checked the input energy. Okay. So that is the thing. Now this needs lesser output energy, to estimate the states. Now this direction needs more output energy to estimate the states. Okay. So that is what it means. Or basically you need to have more measurements for measuring states along this direction for more interval of time. Okay. That's what it means. Now what is left in this which is not there? I mean everything is the same. Okay, so now we will look at your decompositions. Okay, so let us look at decompositions. Okay, so if the system is unobservable, okay, let's say x dot equal to ax plus bu doesn't make any difference, y equal to cx, okay, is unobservable with the rank of your observability matrix equal to some p which is less than n, okay. Then you can write a bar equal to a observable, right, a observable 0, a unobservable, a 2 1, okay, where 2 1 is some coupling matrix, okay. So just a second, let's just write it like this. Yeah, so that's thing. And b bar is b observable and b unobservable, and c bar is c observable 0, okay, where a naught is in R p cross p and au is in R n minus p cross n minus p, okay. So what is the transformation? Transformation is given by z is T inverse x, okay. When z is T inverse x, z dot is equal to T inverse x dot, which is T inverse ax plus bu, okay. So so you can write this is equal to T inverse a x plus bu. Now I will write a as T times z plus T inverse, there is a T inverse here, bu. So now I will take this as a bar and this as b bar, okay, that's it. And y equal to cx, which is same as c times t times z, which implies c bar is equal to c times t, okay. So that's how you get the decomposition. Now the main, I think main doubt comes, how do you get t, okay. I think most of you will have a doubt on how to get the t, because for controllability we took the linearly independent columns of the controllability matrix, because that represent the image of the. So how do you find the image of a basis of the column space? Is same as image, right? So how do you get that? You take the linearly independent columns of a matrix. Now the thing is, here we are not looking at the image, we are looking at the kernel, okay. So what you have to do is, you take the CCA, for example, I will just take a 2 cross 2 system, CCA, which is your observability matrix, and you look at the where T is equal to, I will just write it as V and VO bar, okay, VO bar, where VO bar is the basis of unobservable subspace, okay. So let's take the previous case where it was 0 0, I think it was 1.5, I don't remember, but I think let's take it as this. What is the basis for the unobservable subspace? It is 1 0, correct. So now what is T equal to? 1 0, okay, and what is the other vector which you can use? 0 1, okay. So that's how you construct this T. You have to first choose the unobservable subspace, the basis of the unobservable subspace. You can't just take the columns of the observability matrix, because you know, you have to look at the kernel, not the image, okay. This time it's the dual. So this is your T. We'll look at a problem which we'll solve using MATLAB. So I will show you how to get the T matrix. So let's take a matrix which is 3 cross 3 now. I'm taking A as 0.2, 0.1, 0.7, 0.4, 0.4, 0.2, 0, 0.1, 0.9. Okay, I hope you have seen such matrices before in like week 1 or so. What is the row sum of this? Row sum is 1, okay. Sum of rows is 1. If you see, all sum of rows is 1, okay. So these are something called row stochastic matrices, okay, row stochastic, and they appear in Markov chains and you know, Markov decision processes and things like that. You would have heard of them in reinforcement learning and things like that. So these are row stochastic matrices, and one of their properties, their eigenvalue is 1, okay. The eigenvalue is the 1, and that's the largest eigenvalue. I'm just saying, but we won't go into all that right now. I'm just giving some, you know, So this is, I'm taking C is equal to this value. Okay, C is my 1 0 minus 1. So what is y equal to x1 minus x3? Okay, y is x1 minus x3. So I'll just write the observability matrix, okay, which is same as C CA square, okay, which is equal to 1 0 minus 1. Okay, you can compute C times A as 0.2. Okay, so 0.20, correct, and what is C times A again? Minus 0.2. Okay, now if you again compute this, you will get 0.04. Again, if you multiply this row with this matrix again, what will you get? 0.04, 0, 0.04, correct? Okay, so that's your matrix. Now the thing is, what is the rank of this observability matrix? So there is one 0 column, which means the rank is obviously not 3, and these two are dependent. One is the negative of the other, so which means rank is just 1. Okay, so which means the kernel, the dimension of the kernel of the O matrix is 2. So there are two states which are not observable. Okay, so now how do you find the T? The transformation. The transformation, you have to go to the dimension of this, you have to pick two vectors in the kernel which are linearly independent. So it's very easy in this case. One vector is 0 1 0, correct, because if I multiply 0 1 0 here, it will be 0. Okay, and the second vector, what can you think of? It is 1 1 0 1, correct, that is also 0, because if I add these two, then it's 0, so it's 1 0 1. Now how can I complete this? I can just write 0 0 1. Okay, now if I take this as T and write A bar is T inverse AT and B bar is T inverse B, and C equal to, okay, so sorry, there is no B bar here, C bar equal to C times T, then you can actually see that. But before that, we will go to MATLAB and see if it's actually true. Stop sharing, just a second, just share my MATLAB. Okay, I hope it's visible. So yeah, okay, so my A matrix is equal to 0.2, 0.1, 0.7, 0.4, 0.4, 0.2, 0, 0.1, 0.9. Okay, C is 1 0 minus 1. Okay, now to find the observability matrix, you can write O equal to OBSV of A comma C. Okay, so I'll just run this for now. Maybe I'll just remove this colon, and so that you can print. Okay, so this is my observability matrix. I'll just close all, clear all, CLC. Anyways, yeah, so this is my observability matrix. Now rank of O, I'll just print that also. Rank of O is 1, so which means there are two of them. Now so I have to write the T matrix. So what is the T matrix that I got? T was just take that, just a second. T matrix is 0 0 1 0 1 0 1 0 1. Okay, so that's my T matrix. Now if I check the rank of T, it's 3. Okay, rank of T is 3, so which means I can use this. Now I am writing A bar equal to inverse of T times A times T, T inverse AT, and B bar equal to inverse of, okay, so again, sorry, there is no B bar. So C bar equal to C times T. Okay, now if I just, so here, what is my B bar, value of B? So if you see, it was this first block is just 0.2, that is your observable part, okay, because you just had one block or one state which is observable. So this is your one block, this is your matrix of zeros, and this is your, this 2 cross 2 is your unobservable part, this is your coupling part, okay, where your unobservable and the observable terms are coupled, okay. And if you see your C bar, this is -1 0 0. Yeah, if you can take, you can just take this as negative. I think it's a negative there, I missed a negative sign somewhere, so maybe that's why. I think I missed a negative sign inside. 101, yeah, maybe that's why. Okay, so yeah, C bar, this negative sign doesn't matter because finally it's, you know, if I take one of them as negative, let's say, will that work? Okay, so yeah, that doesn't work, I guess. If I take this as negative, okay, I mean that negative sign doesn't matter here. So yeah, so that's the thing. Now, so this is your A bar. Now let's, yeah, so now next thing is, so there is an easier way to get this. So I'll just tell you the thing. So you just take A bar, B bar and C bar. I'll tell you why I put B bar also, it's not a mistake. So OBSVF of A, I'll just give some random B, it doesn't matter, B and C. Okay, so, oh, it's a 3 cross 3, sorry, 1. Yeah. So what I get is, you know, I get the transformed one, okay, A bar, B bar, forget B bar, it's just a junk value, and C bar. So now actually the system gives you always transpose, so you have to take the transpose here. Like in your stability also, this is A transpose, and yeah, so if you take A transpose, wait a minute, I think it's not A transpose, so yeah. So here the thing is, this block is the zero matrix, this is your observable part, okay, and this 4 cross 4 is unobservable. Basically MATLAB uses a different, you know, T inverse. So I think it takes the transpose of the T, I'm not sure, but the blocks are swapped, that's all, okay. The one block is here, the other block is here. In you know, the unobserved block comes first in MATLAB, the observable part comes later, okay. Same as for C, this thing is for the observable, but in our theory we saw that the first values should be, you know, 1, okay. So MATLAB actually switches that, but you get the point, right? So the code for that is OBSVF of A, B, C, and I think you can get the T matrix also using this. You can check the documentation, A bar, B bar, C bar. You have to just give some value for A, B for now, because we are not looking at B. I'm just giving 1 1 1. I don't know if it's controllable also. So that's the thing. So now you have, yeah, you'll get A bar as this. So it's just swapped, okay, the blocks are just swapped, otherwise it's the same, okay, because it's similar, right? Finally we just have to look at the eigenvalues which are observable, because similarity doesn't change that. It can change the matrix but not the eigenvalue, so that's why. So yeah, so that's the case. Yeah, just like in last class, you can find the Gramian also, okay. So if you find the Gramian, you just have to type gram of, so I'll just have to declare first sys equal to some system equal to ss of A, I'll just declare some B and C, okay. What is the thing, is there some issue? I think think I did that earlier, right? I think here, oh, D also I think I have to give. This is 0. Yeah, okay, I just have to give D also. So anyways, so that is my system. Now how do I find the gram mean? Gram of, I just have to write gram of system, and in brackets you have to give O for observability, C for controllability. So if I just, oh okay, I think I gave A as unstable. So let me just try giving A times 0.1. Will that work? Okay, so A as unstable dynamics. If I just give a random 0.2, 0.3, 0.4, 0, 0.2, 0.3, 0.4, and 0, 0, 0.1. Okay, now if I check, yeah, that's what. So the gram mean cannot be computed for unstable dynamics, just like what we saw in controllability case. So okay, again, okay, if someone, I think it's the continuous time gram mean, that's why. So if I just give negative here, it should work. Negative, 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 and sys and gram mean. Yeah, so if I give negative, it works. So this is my gram mean, which is, you know, as t tends to infinity. Okay, so you can get the gram mean for observability also using this line of code. If you want to do the entire thing, you can just, the code is already uploaded in the folder, so you can just check that, and this A matrix, B matrix you have to give, and C also you will have to give. So you find the gram mean by E. So this is my state transition matrix. Now observability gram mean, you just have to write phi transpose C transpose C phi. Okay, so and integrate it from, let's say, 0 to 5. That's how you have to give. So you'll get the observability gram mean, that's all. So the code is already there, you just have to change it to, you know, according to your according to the observability thing. So now we look at detectable systems. Just a second, I'll just switch my screen. So now share, yeah, okay, so just a second. Okay, so now we wrote this is observable 0, A21, A unobservable. So this is nothing but Z0, or I'll just write the same variable, X observable and X unobservable is equal to X dot, the derivative is X unobservable, and Y equal to CO times XO, correct? Y equal to CO times XO. So what is my XO dot equal to? A observable, X observable. Okay, good. What is this? A21 X observable plus AU X unobservable. So this is nothing but XU is equal to e raised to AUT XU plus some integral A21 again. So e raised to AUT A21 X naught. Okay. So this is something like an input to this term. So it's something like a forcing term. Now the problem is, if XU blows to infinity, okay, then what happens? So if this goes to infinity, then you can't actually just a second, I think, yeah. Yeah, so this is your unobservable dynamics. So your unobservable dynamics can blow up, right? And you won't even realize that because it doesn't come inside your, inside your output. Okay, there can be some dynamics which blows up and you won't even know, and these dynamics can be coupled in some way to your observable dynamics. Okay, so which means if your AU matrix is Hurwitz, you are guaranteed that XU will go to 0 as X0 also goes to 0, okay, because there is a term here, correct. So if X0 goes to 0, XU will also go to 0 only when AU is Hurwitz. Okay. So if AU is Hurwitz, then the system is called detectable. Okay. The system is called detectable when AU is Hurwitz or it's a stability matrix. Okay. So you first decompose. So the only way to check is, so one way is to decompose and check AU. Second way is using your eigenvector test, which means eigenvector of A which are positive real part must not belong to the eigenvector. So I am just writing this as bad notation, eigenvector of A which have real part lambda greater than 0 should not belong to kernel of C. Okay. And third is PBH. So the same thing, rank of A minus lambda I should be equal to n for real part lambda greater than 0 for continuous time case. For discrete time, the absolute value should be greater than or equal to 1. Okay. So that's the thing. And for your Lyapunov case, you have A transpose P plus PA minus C transpose C must be negative definite. I think it's it must be negative definite. Okay. If you can find a unique P, there exists a unique P such that this holds. Okay. That's your detectability test. Okay. So now in short, in summary, what we have done in these 2 weeks is you have taken a system. Okay. Let's say your input goes in, this is weak, this is controllability. Okay. Your input goes in, but the input only enters a sub part. Okay. Then there is another part which the input doesn't enter. This is your controllable and this is your uncontrollable. Okay. So I'll just write C bar. Okay, this is uncontrollable. And today's week we saw there is some output coming out which only comes from your observable part, and there is a unobservable part. Okay, this is observability. Okay. Now next week we'll split the system into 4. Okay, basically a combination of all these 2. So we have 4. Okay, we have 4. This is controllable, observable, controllable, unobservable, all the 4 combination. And so where will the control input enter? The control input will enter here, and which all states will affect the output? These 2. Sorry, not these 2, sorry, these 2. Okay, this will affect your states. Now how do you decompose it into 4? That's what we will see in the next week. So as of and the thing is, you have to make sure this part must be Hurwitz. Okay. And there is something called minimal realization also, that's where pole 0 cancellations and all come in. I think you would have done in your basic control course. So that is because of this, the system losing controllability or observability will result in pole 0 cancellations. Okay. So do you have any doubts regarding any assignments or anything? As of now, all the lectures, because this week is pretty straightforward. If you have done the maybe just the T, the computing the T is the only change which there is. Otherwise, it's all dual. Again, that is also dual, but it's a bit confusing compared to your previous one. So do you have any doubts as of now? Yeah.
Just share that code snippet on.
Sure. Yeah, I've shared the, yeah.
I need to remember those function names.
Okay, okay. So
I'm
this
not.
class, I think I have not introduced any codes, because I mean I have not introduced anything new, because it's the same as last class. So it's the same code also. I have uploaded both the codes. So instead of O here, you have to, I think you have to give
No,
C.
there were two functions, OBSV and I think OBSVF.
Okay, okay, this one. Okay, okay, OBSVF. This one. So this is for observable decomposition. So there is a function for controllability also, CTRBF. Okay. So
CTRBF.
CTRB, controllability.
CT.
So CTRB is for computing the controllability matrix, okay, and CTRBF will compute the controllable decomposition, okay. So yeah, yeah, maybe I'll share this code also. Just a second.
Yep.
Observability.
Even if you just share those function names, that will be helpful.
Yeah, yeah, okay. Maybe in the notes itself, I'll just write it down in case, okay. MATLAB commands, okay. So one is CTRB for controllability matrix, okay. OBSV for observability matrix, CTRBF, there is an F, okay, maybe I'll write it properly. CTRBF for controllable decomposition, okay, and OBSVF for observable decomposition. Okay, so that's the only, I think these are the only new ones that I've given. So yeah, so that's the thing. Yeah.
Thank you.
Yeah, for 2x2 systems, I think it's better to do by hand, and for higher order, maybe you can use MATLAB, because you need to get that practice for at least 2x2 systems. So yeah, so yeah, so if there are no doubts, maybe we'll meet in the next class. Yeah, as I said, next class we'll see how to split it into 4, not 2. Okay. So this time we just saw what controllability separately and observability separately. Next class we will see how to split it into all 4 subspaces. Okay. So yeah, so I think I'll see you in the next class. Okay. Thank you.